Hello everyone. So in today's video, we're going to do some more practice using all of the derivative rules that we have used so far or learned so far. So basically, the rules that we've learned thus far, we've been kind of using one of them at a time, right? Okay, we know how to find the derivative of sine, or we know how to find the derivative of x squared. And today we're really going to kind of see how you can have a function that maybe requires a whole different kind of blend of these different rules. So we're going to kind of practice how you can tackle a question and figure out what rule to use when. So before we get into that, I just want to remind you of the new derivatives that we learned in the last video. So the trigonometric derivatives, so these are from last time. So in yesterday's video, we went through the derivatives of sine, cosine, and tangent. And then I asked you on your worksheet to use kind of a similar idea that we did with the derivative of tangent to figure out what the derivatives were for the other three trig functions. So I'll write those down as well. So based on yesterday's video, we saw that the derivative of sine of x is cosine of x. We saw that the derivative of cosine of x is negative sine of x. And then we used the quotient rule together with knowing the derivatives of sine and cosine. Well, because tangent can be written as sine over cosine, we could use the quotient rule to figure out what the derivative is for tangent. And so after doing some simplification, we found that it was secant squared of x. And then the other three that so basically if you write each of these other three functions, so for example, cosecant can be written as 1 over sine. So if you write cosecant as 1 over sine and apply the quotient rule and do all your simplification, what you should come up with is that the derivative is negative cotangent of x times cosecant of x. And then the derivative similarly, so secant is the reciprocal of cosine. So if you write it as 1 over cosine and then use the quotient rule and simplify, you should end up with tangent of x times secant of x. And then the last one, so cotangent, you could actually for that one either write it as cosine over sine, or you could write it as 1 over tangent. It doesn't really matter. And then go through the simplification using the quotient rule, you should get negative cosecant squared of x. So what I would say is you for sure want to have the three on the left memorized. Those are going to come up a lot. The three on the right, I probably wouldn't put them on like a test necessarily, but they definitely will come up on the homework and stuff like that. And when you get to calculus 2, you probably will want to have those memorized. But like I said, I think because you can come up with them using the quotient rule, I just honestly don't even bother memorizing them. Just because they're just 1 over something, it doesn't take that long to use the quotient rule to come up with the derivative. Okay, so let's jump into some examples. So we're going to start with a fairly straightforward one. And then the rest of them will all have something a little bit more interesting or tricky going on. But this is kind of a more straightforward, just like practice using a couple of different rules. So let's say we had cosine of x divided by 2 times e to the x. So how would this, what rule do we need to use for this derivative? Well, it's a quotient, right? We're doing one thing divided by another. And so that tells us we want to start by using the quotient rule. So the way that the quotient rule works is that we start by taking the derivative of the top. And so I'm going to use the same notation that I've been doing in a few other videos. And we'll see today why I think that that's a good way to write it. Basically, we'll see later some examples that there's just a little bit more going on. And I think if you can really kind of organize your work by just saying, okay, I'm first taking the derivative of this, that will help you keep things organized. So the quotient rule, we take the derivative of the numerator and then just multiply it with the denominator. And then from that, we subtract the derivative of the numerator of the denominator times the numerator. And then we divide that by the denominator squared. Okay, so let's go in and actually take these derivatives. So the derivative of cosine we saw in the last video was negative sine of x. And then we're multiplying that with 2e to the x. And then the derivative of 2 times e to the x is still 2 times e to the x, right? Because the derivative of e to the x is e to the x. And then that 2 just comes along for the ride. So we have minus 2e to the x cosine of x, all divided by, so let's write this as 2e to the x times 2e to the x. And so now we can do some cancellation. So like I mentioned, if you have an e to the x as your denominator in a problem with the quotient rule, you're generally going to, or you will always be able to cancel something out because that e to the x is just going to kind of appear over and over in the numerator and the denominator. So in this case, let's factor out from the top a 2e to the x. So if we do that, we're left with negative sine of x minus cosine of x, all divided by 2e to the x times 2e to the x. And so now we see that we can get rid of this 2e to the x. And so we're left with negative sine of x minus cosine of x divided by 2e to the x. And another way that some people might choose to write this that maybe is like a little bit nicer is we could factor out a negative sign, and so then we'd be left with sine of x plus cosine of x over 2e to the x. But I would be fine with you leaving your answer as is. And we will talk about today, I'll point out some examples of like what kind of level of simplification I'm looking for, because especially when trig gets involved, there's usually a lot of different ways that you can write something, and I want to make sure I'm being clear, what my expectation is. Cool, so that is our first example. So next we're going to do an example that I kind of picked out just to show you how much simplification can make a difference. So let's look at this example. So g of x is equal to sine of x times secant of x. So let's do this two different ways. The first way we're going to do it is we're going to use the product rule. And it's not like it's going to be that hard to use the product rule, but then we're going to come back and instead of using the product rule, we're going to simplify it from the get-go. Like basically, you kind of have a choice when you're taking derivatives. You can simplify first or simplify after. And in some cases, there really isn't anything you can do beforehand, but oftentimes there is, and doing that simplification before you take the derivative will just make your life easier. Okay, so let's say we wanted to do this using the product rule. So the product rule tells us that we take the derivative of the first part. So the derivative of sine of x is cosine of x. And then we just multiply that with the second function without taking the derivative. And then to that we add, we're going to take the derivative of the second part. So the derivative of secant is secant times tangent. So that is secant x times tangent of x. That's the derivative of secant x. And that was probably not a good placement for that. And then we're going to multiply that with the first function, which is sine of x. So that was just product rule, right? It looks a little confusing, but it's just because the derivative of secant of x actually has a secant of x in it. Okay, so now let's go through and see what we can simplify. So cosine of x is, secant of x is 1 over cosine of x, right? So we can rewrite this as cosine of x times 1 over cosine of x. So when I say simplify, when we're talking about trig functions, oftentimes it's kind of this game of like going back and forth between rewriting them in terms of sine and cosine. So like, for example, taking secant and rewriting it as 1 over cosine to see if things can maybe cancel out. But then later on, you might actually want to kind of flip it back into being no more fractions, because it's kind of nicer to rewrite things without the fractions at the end. But in the process, it's nice to kind of break things down just so you can see what goes with what. So similarly here, so secant is 1 over cosine. Tangent is sine over cosine. And then we just have a sine, right? Just a sine of x. Okay, so let's see what this all simplifies to. So the first part here, this is just going to equal 1, right? Because we have cosine over cosine, so that's just 1. And then let's see what's going on over here. So we have sine squared on the top, right? Because we have 2 sines being multiplied together. And then we have 2 cosines on the bottom. And so sine over cosine is tangent. So another way of writing this is 1 plus tangent squared of x. And this can actually be simplified even further. So there's, I mentioned, I think probably in yesterday's video, the Pythagorean identity. So maybe let me just kind of write that as a side note here. So there are 3 different Pythagorean identities for trigonometry. So the most important one that you definitely want to know is that if you have sine squared of x plus cosine squared of x, that's always going to equal 1. Then there's 2 others, and the way that, like, I honestly don't really memorize them, I just memorize this one, because the way that you can get the other 2 is you can just take this equation and go through and divide everything either by sine squared or by cosine squared. So for example, if we take this equation and we divide every single part of it by sine squared, we're going to end up with 1 plus, so cosine squared over sine squared, that is cotangent squared. And then if we do 1 divided by sine squared, that gives us cosecant squared. So that's the second Pythagorean identity. And then if we go back to this first one and we divide everything instead by cosine squared, then we get tangent squared of x plus 1 is equal to 1 divided by cosine squared is secant squared. So these are definitely good to know. And like I said, if you're taking Calc 2, this stuff will, like, there will be a lot of trigonometry involved, and knowing these trig identities will be really useful to you. So basically, we just figured out that in this third one that we wrote down, that tangent squared plus 1 is equal to secant squared. So that means that our derivative is secant squared of x. So let's actually now go back and see if we could have done this differently. So let's, instead of doing the product rule, let's go back to our original function and just simplify it and see from there what we get as our derivative. So the second method is to simplify first. So first meaning before taking the derivative. So if we have g of x is equal to sine of x times secant of x, well, we can rewrite that as sine of x times 1 over cosine of x. And then that's the same thing as sine of x over cosine of x. And that's the same thing as tangent of x. So our original function all along was just tangent of x. It just looked different. And so now that we know that our function is tangent, well, we know that the derivative of tangent is just secant squared of x. So we got the same thing either way, but I think hopefully you agree that the second way was a lot faster. Okay, so I'm going to get into another example now where we're going to use the same idea of simplifying first. And in this case, we're not actually going to do it both ways. We're just going to do the simplification because if you don't simplify it first, it would actually be, I think, pretty challenging to do the simplification after. And there's one like this, by the way, that's really similar to this on your homework. So that's the reason I chose this one. So let's say we have y is equal to 5x times cotangent of x divided by cosecant of x. So let's simplify this first. And sometimes maybe you'll try to simplify and it won't work, but I think it's always worth a shot especially when you're dealing with trig. Just see if you can rewrite everything in terms of sine and cosine and see if anything kind of comes out from it. So cotangent is the same thing as cosine over sine, right? So I'm going to write it like this. I'm going to say 5x times cosine of x over sine of x. And actually, I think maybe it'll be clearer if I write it this way. I'll just put the 5x. It doesn't matter if you put the 5x in the numerator with the cosine or outside, but let's just put it actually in the numerator. So I rewrote cotangent as cosine over sine and then just multiplied it with the 5x. And then in the denominator, we have 1 over sine of x, right? Because cosecant is the same as 1 over sine. So what's going on here? Well, there's kind of two ways to do it. So either you can take whenever you have a fraction divided by another fraction, you can, instead of dividing, multiply by the reciprocal. So instead of dividing by 1 over x, we can multiply by sine of x over 1. Alternatively, it's kind of a nice thing to just recognize in general. So in general, if you have something that looks like a over b over c over b, that's always going to simplify to a over c because of basically what we just did here. If they have the same denominator, then they'll kind of cancel each other out. Okay, so what happens when we simplify this? Well, now we have a sine and a sine that are going to cancel out, and we'll be left with just 5x times cosine of x, which is a whole lot simpler than what we started with, right? If you had not simplified this, you would have to use the quotient rule and the product rule because the numerator is a product, right? And then you'd also have to use the quotient rule. And we'll actually do an example like that later on that can't be simplified, and it's not like that crazy, but in general, the fewer rules you have to use, the better. So by simplifying this, we got it down to something where now all we have to use is the product rule. So we're going to use the product rule in this case. And so our two functions are 5x and cosine of x. So we're going to first take the derivative of 5x, and that is 5. And then we're multiplying that with cosine of x. And then to that, we're going to add the derivative of cosine of x. So that's negative sine of x times 5x. And so that simplifies to be 5 cosine of x minus 5x sine of x. And typically, I think most people kind of follow this convention of if you have something like sine of x times x, that you put the x before the sine, but it's fine if you want to put it after. It doesn't, if you had left it like this, there's nothing wrong with that. It's just kind of more traditional, I think, to write it the way that I did here. Okay, so now we're going to get into two examples that are a little bit more complicated. This one I think initially looks complicated, but we were able to simplify it. These next two are ones where you really can't get around the complicatedness. So first one we're going to do is going to be x squared times e to the x times sine of x. So there's one kind of like this on your homework where so what's going on here, it's a product, but it's not just the product of two functions, it's actually the product of three functions. So how are we going to deal with this? The product rule only tells us how to take the derivative of a product of two functions, right? But what we can do is we can just split this into two functions to start with. So you could do it either way, but maybe let's group these two together. So this is going to be like function 1, and this is going to be function 2. So we're going to start by using the product rule with the functions x squared e to the x and sine of x. We're going to think of those as our two functions. But what we'll see is that when we go through using the product rule, we're actually going to have to use the product rule again. And this is where I think that notation I keep talking about and blabbing on about, I think will actually really help us in this case. So how does the product rule work? You're supposed to take the derivative of the first function and multiply it with the second function. So I'm just going to use this notation as kind of a placeholder. So we know that we're supposed to take the derivative, we know we're supposed to take the derivative of the first function, which we chose to be x squared e to the x. So I'm just going to write it like that, derivative of it. And then we multiply that with sine of x. And then we're supposed to take the derivative of sine of x and multiply it with the first function, which was x squared e to the x. So now we can go in and take the derivatives here and here, and we'll see that in this case, or in the second step, we're going to have to use the product rule again, where now we're going to be thinking of these as our two functions. So next we're going to, in order to find the derivative of x squared e to the x, we're going to use the product rule again with functions x squared and e to the x. And hopefully I'm not getting off screen. I know it cuts off somewhere close to where I am, so maybe I'll nudge it over a little. So I think like the thing that students have the most trouble with in calculus, in my experience teaching it, is functions that are complicated. And we'll get to functions that are actually significantly more complicated than this starting like next week. Students have a really hard time, I think, figuring out like what to do first. Like they'll look at something and say, I can tell it's a product, but I don't really know like what order to do things in. And so I really think using this prime notation can help you kind of keep track of that. Because we're going to have to use the product rule again, but we're not just going to kind of willy-nilly use the product rule. We're going to specifically use the product rule to replace this part here. Everything else is going to stay the same, right? Because everything else is either we're not taking the derivative of it, right? This part, there's no derivative. This part, there's no derivative. And then the other derivative, well, that one we can take without the product rule. So we're really just using the product rule on this one little part, and then just kind of inserting the derivative we get into our kind of initial framework for the derivative. So we can go in, and where we had written this x squared times e to the x prime, now we can actually take the derivative of that. So what's the derivative of x squared times e to the x? Well, we start by taking the derivative of x squared, and that's 2x, and we multiply that with e to the x. And then to that we add the derivative of e to the x, which is e to the x, and we multiply that with x squared. And then we multiply that with sine of x. So now from here we just kind of continue with what we already had written down. And then the derivative of sine of x is cosine of x. And then we don't need to take the derivative of this part, right? Because we already kind of finished that part of the derivative. That came from the original product rule we did. And so the only thing we still had to take the derivative of was the part that we had the prime on. And that's why, again, I think that's a good way to kind of initially set it up. So let's clean this up a little bit. If you wanted to, you could distribute the sine of x. You don't really have to. Maybe let's just do it. Personally, I tend to like to distribute stuff, but it really doesn't matter. You could leave it factored if you like that better. So we have 2x e to the x sine of x plus x squared e to the x sine of x plus x squared e to the x cosine of x. So that's our final answer. So kind of a crazy function. And that's something that I think I was just thinking about today, that like when you're in pre-calculus, most of the functions that you see are kind of only one type of function, right? It's like it's a polynomial, or it's a trig function, or it's an exponential function. And one of the things that is probably kind of new to you in calculus is we're going to be dealing with a lot of functions that kind of combine the familiar functions in different ways. And so the derivatives are also going to be these kind of crazy mixes of all these different types of functions that you've learned about in the past. Okay, so we're going to do one more example together. And I feel like I have been doing a lot better with this, with my handwriting staying straight. And for some reason today, it's going up again. So I'll try to keep it under control in this last example. So let's say that we wanted to find the equation of the line tangent to f of x is equal to x e to the x over cosine of x. And we're going to do it at x is equal to 0. So if we're trying to find the equation of a tangent line, we want to start by taking the derivative, right? Because we're going to need the slope of the tangent line, and the way we get the slope of the tangent line is from the derivative. So in order to take the derivative, we want to kind of look at this function, and you might see multiple things going on, right? We see some division going on. We also see that x is being multiplied with e to the x. So it's kind of like there's a quotient and a product going on. But if you kind of just look big picture at this function, what is it overall? Like, what does it look like the most? It most looks like a quotient, right? It's something divided by something. And so that kind of signals to us that we want to start by using the quotient rule. And then along the way, we'll have to use the product rule. But because our at least the way it's written right now, our function is not itself a product. It's a quotient, right? It's something divided by something. So we're going to start by applying the quotient rule. And again, we're going to use this kind of placeholder notation so when we go in and use the quotient rule, the first thing we do is we take the derivative of the numerator, right? So I'm just going to write x e to the x prime as a placeholder to remind us that we're going to need to take the derivative of that numerator. And then from that, we subtract taking the derivative of the denominator and multiplying that with the numerator as is. And then we're going to divide that by cosine of x squared. Okay, so now we can go in and use the product rule on this, right? So for this, we have to use the product rule. So in the next step, when we write down the derivative, we're not using the product rule on anything else. We're just kind of replacing this part that I circled in purple with the derivative that we would get using the product rule. So what's the derivative of x times e to the x? Well, it's going to be, the derivative of x is just 1. So it's going to be 1 times e to the x. And then to that we add the derivative of e to the x, which is just e to the x. And we multiply that with x. So all I did was take that part that I circled in purple and just write that derivative. And then everything else is the same because everything else we kind of finished. I guess the one other thing we didn't finish is we didn't take the derivative of cosine. So the derivative of cosine is negative sine. So we'll simplify that in the next step. And then we're multiplying that with x e to the x. All over cosine of x squared, which let's rewrite that as cosine squared of x. Okay, so let's simplify this a little bit. So we have e to the x plus x e to the x times cosine of x. And then that's plus x e to the x times sine of x. All right. So in this case, if we think about what we were actually supposed to do in this question, we were just asked to find the equation of the tangent line at a particular value. So in this case, we could actually just go ahead and plug in our number. So we're looking for the derivative at x is equal to 0, right? So we could go ahead and just plug that in right away. But I actually want to go through the process of kind of simplifying this with you, just because I think it's a good example of a function that there's a lot of different ways to write it, and I just want to kind of show you what I think personally is a slightly nicer way of writing this function. So again, if you were doing this on your homework or on a test or something, and you didn't need to just, if I never asked you to actually write down what f prime of x is in its simplified form, it would actually probably be faster to just plug 0 in at this stage. But just for the sake of practice, I do want to go through actually simplifying it. So how would I go about simplifying this? Well, basically looking at this, I can see that here we have a cosine and a cosine that we can do some stuff with. And then here we have a sine and a cosine that kind of seem like they might interact. And so that's what kind of makes me think, okay, maybe there's a better way to write this. So I'm going to split this into two fractions. So I'm going to rewrite this as e to the x plus x e to the x cosine of x over cosine squared of x plus x e to the x times sine of x over cosine squared of x. So now what can we do? Well, here we have cosine over cosine squared, so we can cancel out one of those cosines. And so we'll be left with e to the x plus x e to the x times 1 over cosine of x. So I kind of pulled that 1 over cosine of x out because that we're going to turn into secant, right? Because that's what 1 over cosine is. And then for this other part, well, there's a few different ways that you could think about it, but I would probably do this. So we have x times e to the x. Then we can split up this cosine squared into two cosines. So we can rewrite this as sine of x over cosine of x times 1 over cosine of x. So let's see what this gives us on the next step. So now we can write this first part as e to the x plus x e to the x times secant of x. And this next part we can write as x e to the x times tangent of x, right? That's what sine over cosine is. And then times secant of x. And then if you wanted to, you could then distribute this part, and I'll just do it because I don't know, for some reason it bothers me when only part of something is factored out. So let's just be consistent here. Plus x e to the x. So why am I doing this? Like, why is it worth it to go through all this work of rewriting this? Well, it kind of depends what you're doing. So I don't want to say that like, oh, this way of writing it is definitely better. It really depends on what you're doing. Kind of like how we talked about with polynomial, or not polynomials, but like, you know, if you have, let's say, x to the negative 1/2, you know, is it better to write it as x to the negative 1/2, or is it better to write it as 1 over square root of x? And it really depends what you're doing. So one reason that you might want to be able to rewrite things so that it's in terms of, basically so that there's no fractions, is because then, let's say you had to take another derivative. In this case, that would be a pretty complicated function, but in some simpler cases, that might be a pretty legitimate thing to ask you to do, to take the second derivative. So even though this looks pretty complicated, taking the second derivative of each of these parts would not be that hard. This last part would be annoying because it has actually 4 things you would have to take the product of. But in general, like having these trig functions written in terms of just normal trig functions instead of having all this division going on is a lot easier. So like, you know, would you rather have to take the second derivative of this or of this? And I know they both look complicated, but I think the bottom one would be easier to work with because you can just look, okay, I know what the derivative of secant of x is, or you can look it up if you don't remember. Whereas in this first one, you would have to do a lot of quotient rule and product rule. There'd just be a lot of different stuff going on. Okay. And I'll try to make it clear on, like if it's a test or a quiz or something, I'll make it clear what my expectations are in terms of simplification. Okay, so here's our derivative, but this isn't really our end goal. Our end goal is to find the equation of a tangent line. So the next thing we want to do is we want to find the slope at x is equal to 0 because we're looking for the equation of the tangent line at x is equal to 0. So luckily, 0 is a pretty nice number to plug into this function. So e to the 0 is going to be 1. So secant of 0, so that's 1 over cosine of 0. Cosine of 0 is 1, so we get 1 over 1, which is 1. Next part is just going to be 0. We don't even have to write everything out. I'll just put it, but if it's 0 times some other stuff, you don't care what that other stuff is. And then same thing with this last part. So you would have, and I'll just write it just so you can have it written down, but you don't really need to do these ones. So tangent of 0 is 0, secant of 0. So really all this comes out to just be 1. So that's the slope. And then we want to find the point that this line goes through. So the original function was x times e to the x over cosine of x. So we just want to plug in 0 to that. So f of 0 is going to be, 0, right? Because the numerator was x times e to the x, so it's 0 times 1 over, cosine of x, so that's 1. And so we just get 0. And so that means that it goes through the point 0, 0. So here's our slope, here's our point. And so to write down the equation, all we need to do is kind of put those into place. And actually, in this case, you don't even need to use point slope form. You can really just kind of use y equals mx plus b form. And because the line goes through 0, 0, its y-intercept is 0. And so that means the equation of the line is actually just y is equal to x, right? Y is equal to 1 times x. That is a line that has a slope of 1 and passes through the point 0, 0. All right, so that is it for today. We'll be doing definitely more stuff along these lines next week. So we'll learn another rule that's called the chain rule that helps us take derivatives of functions that are composed with each other rather than being added, subtracted, multiplied, divided. And yeah, we'll see basically a lot more stuff of this flavor of like taking a function that looks kind of complicated and kind of breaking it down and figuring out what we need to do in order to take the derivative. All right, I will see you next week and have a great weekend.